So a long time ago in the 17th century, there's a German guy called Johannes Kepler. And what he did was, by working with other scientists like Tycho Brahe, they looked at the orbits of all the planets that were going around the sun. And basically, there's this guy called Galileo that you might have heard of, and he basically ignored the work of Kepler at the time because they were around at the same time. But one guy who really was sort of used some of the ideas of Kepler for his other laws was a guy called Newton. And basically, the work that Johannes Kepler did on gravity and basically the orbits of planets fed into the work that Newton later did on gravity. And basically, he has three laws which are sort of named after him. And it's basically from looking his sort of observations and then his actual mathematical work of looking at the orbits of planets around the sun. So Kepler's first law basically states that the orbit of a planet is an ellipse with the sun as one of two foci. And effectively an ellipse is just this kind of squash circle, this kind of egg shape. And if we think about the two foci, so here and here, the distance from this one and this one added together up to the edge at any point on this ellipse is always equal to a constant value. So that's what really makes it an elliptical shape. And often in books it's kind of exaggerated massively, and you sort of see this kind of real kind of squashed egg shape actual orbit of the Earth. Now that can't be true, because if we had that, then the sun would get bigger and smaller at different times of the year. In actual fact, as the Earth orbits around the sun, it only changes by about sort of 3%, so it's pretty much a very small ellipse, okay? And effectively what we have is we've got the sun as one centre, and we've got a point just outside the sun as well, which is our other point of the ellipse. And basically this is Kepler's first law. But now on to his second and his third. Okay, Kepler's second law says that a line segment joining a planet and the sun sweeps out an equal area during equal time intervals. Now what I've got here is a real kind of massive ellipse here with the sun as one foci, and what I'd like to consider is maybe not just a planet, but maybe perhaps some kind of comet or something like that. And what it does is it moves a long way away from the sun, and then it comes in quite quickly, moves around it and goes back out into deep space. And effectively a line segment, so here we've got the position of a comet at different times. This just joins basically where the sun is down here with one of these. So if I join the line segments in, now this rather poor drawing, it's not exactly accurate, but effectively what we're saying is that as a comet moves from here to here, or from here over to here, as it moves along, there's this kind of chord thing that kind of sort of sweeps out. And effectively what we say is that this area here is going to be equal to this area here, provided the time from here to here is exactly the same. What does that mean? Well, effectively, if it's going, when it gets closer to the sun, it has all this potential energy, which it then exchanges into the form of kinetic energy, and that means its velocity increases. So in the same time period, which is a time t, it will move a greater distance, and therefore it's moving at a faster velocity. And then it moves really quickly around the sun, and then it kind of, as it goes further away, it kind of slows down as it gains potential energy, and then we have this kind of interchange between kinetic and potential. And this is something that Kepler found out. So basically this line segment joining the planet over to the sun, and again we've always got a capital S for sun, capital E for the Earth, and a capital U for the universe. It sweeps out an equal area during equal time intervals. And that's Kepler's second law. Okay, Kepler's third law, and again, apologies, I can't quite do this to scale, but basically Kepler's third law was when he looked at the various different planets and their time periods, okay? So the time period T was their time to do one complete orbit of the sun, and also he looked at their distances away from the sun, which we're going to call R. And basically he found that there's a link between the time period for one rotation and the radius from the sun. And basically things that were further away took longer to go around the sun. Well, we kind of know that. But basically what he said was that the time period squared is proportional to the radius cubed. And just written out, we can say that the square of the orbital period t is directly proportional to the cube of the average distance from the sun, which is r cubed. And this was a long time before Newton did his work on gravitation. And I'd like to show in the next bit of this video about how you can actually show that yourself using Newton's laws, and also your work that you should know by now about centripetal force. So let's maybe consider the Earth going around the sun, and it's got a certain mass, which I'm going to call little m, and also we have the mass of the sun, which I'm going to call big M. They're separated by a distance from their centre of masses of r and this is going at some point with a tangential velocity of v. Well, what we know is that from Newton's law of gravitation, the force between these two objects is going to be equal to gmm over r squared. Okay, but we also know that the force on this thing here, causing it to move in this circular path, and we're going to assume a perfectly circular orbit at the moment, this force, the centripetal force, is equal to mv squared over r. And effectively, it's this gravitational force here that provides the centripetal force. So what we can then do is equate the two together to say that gmm over r squared is equal to mv squared over r. And what you can see now is that, first of all, the mass of the Earth is basically cancelled off both sides, and we can also cancel the r down here. So what we can then say is that gm over r is equal to v squared. But what do we know about the velocity of this? Well, so far there's no t and so on, and we don't even have an r cubed. But what we know is that the velocity of the Earth is going to be equal to its circumference, the distance it travels in 1 year. And the circumference of this is going to be equal to 2 pi r, and the time it takes to go this one rotation around the Earth is equal to 1 Earth year. We can then say, if we square both sides of this, we can say that v squared is equal to 2 squared, which is 4, times pi squared r squared over t squared, and we can then substitute this back into here to replace the v term. So what we can then say is that gm over r is equal to 4 pi squared r squared over t squared. And if we rearrange this to make t the subject, so what I'm going to do is I'm going to bring this up here to say t squared is equal to 4 pi squared over gm multiplied by r squared times r, which is r cubed. And what we can see now is that provided we have maybe the same gravitational constant, which we must do, we've got the same mass of the Earth, and then 4 pi squared as well, everything here inside these brackets is a constant. And that means we can say then that t squared is proportional to r cubed. And it's only really, this is basically what Kepler found out, and it's only really later that this is what Kepler found out that then allowed Newton to look at his universal law of gravitation.